Good day, everyone. This is Teacher Riza. Our topic to discuss today is Introduction to Logarithm, wherein we're going to discuss common logarithm, natural logarithm, Richter scale, sound intensity, and pH level of water. With learning competency, the learner represents real-life situations using logarithmic functions. By definition, let A, B, and C be positive real numbers such that B is not equal to 1. The logarithm of A with base B is denoted by log of A to the base of B and is defined as C is equal to log of A to the base of B, or log of A to the base of B is equal to C. If and only if A is equal to B raised to C, or B raised to C is equal to A, wherein B is the base, C is the exponent, and A is the answer. So in log A to the base of B is equal to C, log is logarithm, A is the answer, B is the base, and C is the exponent. So therefore, for us to easily recall what is log A to the base of B is equal to C, that is the logarithm of the answer to the base is equal to exponent. For example, log of 8 to the base of 2 is equal to 3, wherein 2 is the base, 3 is the exponent, and 8 is the answer. So therefore, in exponential form, that is 2 cubed is equal to 8. Common logarithm are logarithms with base 10. Log of x is a short notation for log of x to the base of 10. For example, 10 squared is equal to 100. 10 is the base, 2 is the exponent, and 100 is the answer. So therefore, in logarithm, that is the logarithm of 100 to the base of 10 is equal to 2. So in common logarithm, we're not going to write base 10 anymore. But instead, we can write this into log of 100 is equal to 2. Means that the logarithm is in base 10. Natural logarithm are logarithms to the base e, wherein e is approximately 2.71828 and denoted by ln means natural logarithm. In other words, the natural logarithm of x is another way of writing log of x to the base of e. For example, e cubed is equal to x. Writing that into logarithm, that is log of x to the base of e is equal to 3. So another way of writing this is log to the base of e is a natural logarithm. So we have the natural logarithm of x is equal to 3. Writing exponential form into logarithmic form. For example, we have 5 cubed is equal to 125. 5 is the base, 3 is the exponent, 125 is the answer. So in logarithmic form, this is the logarithm of 125 to the base of 5 is equal to 3. Number 2, 4 raised to 0 is equal to 1. 4 is the base, 0 is the exponent, and 1 is the answer. So therefore, in logarithmic form, this is the logarithm of 1 to the base of 4 is equal to 0. Number 3, 7 raised to negative 2 is equal to 149. So that is the logarithm of 1 over 49 to the base of 7 is equal to negative 2. Number 4. 7 raised to b is equal to 21. So this is the logarithm of 21 to the base of 7 is equal to b. Number 5. 10 squared is equal to 100. This is in base 10, so therefore, this is a common logarithm. So we can write this into log of 100 to the base of 10 is equal to 2. Or log of 100 is equal to 2 because this is a common logarithm in the base 10. Number 6. E squared is equal to x. So base e is a natural logarithm. So we can write this into the logarithm of x to the base of e is equal to 2. Since logarithm to the base of e is a natural logarithm, so therefore, we can write this also into natural logarithm of x is equal to 2. 2/3 raised to 3 is equal to 125. So this is the logarithm of 125 to the base of 2/3 is equal to 3. Negative 2 squared is equal to 4. So this is log of 4 to the base of negative 2 is equal to 2. 0.1 raised to negative 4 is equal to 10,000. So this is log of 10,000 to the base of 0.1 is equal to negative 4. For this time, we're going to write logarithmic form into exponential form. Number 1, log of m is equal to n. There is no base, so therefore this is a common logarithm, means in base 10. So in exponential form, this will be now 10 raised to n is equal to m. Number 2, log of 81 to the base of 3 is equal to 4. 3 is the base, 4 is the exponent, 81 is the answer. So therefore, 3 to the 4th power is equal to 81. Log of 5 to the base of square root of 5 is equal to 2. Square root of 5 is the base, 2 is the exponent, and 5 is the answer. So therefore, that is square root of 5 squared is equal to 5. Number 4, log of 64 over 27 to the base of 3/4 is equal to negative 3. 3/4 is the base, negative 3 is the exponent, 64 over 27 is the answer. So therefore, we have 3/4 raised to negative 3 is equal to 64 over 27. Number 5, log of 2 to the base of 4 is equal to 1/2. Or that is 4 raised to 1/2 is equal to 2. Number 6, log of 0.001 to the base of 10 is equal to negative 3. So this is 10 raised to negative 3 is equal to 0.001. Number 7, the natural logarithm of 8 is equal to a. Since this is a natural logarithm, so therefore the base is e, and a is the exponent, and 8 is the answer. So therefore, in exponential form, this is e raised to a is equal to 8. Now, how we're going to represent a real-life situation using logarithmic functions? Some of the most common application in real life of logarithm are the Richter scale, sound intensity, and pH level. Richter scale. In 1935, Charles Richter proposed a logarithmic scale to measure the intensity of an earthquake. He defined the magnitude of an earthquake as a function of its amplitude on a standard seismograph. The following formula produces the same results, but is based on the energy released by an earthquake. Earthquake magnitude on Richter scale is R is equal to 2/3 of log E times E over 10 raised to 4.40, where E is the energy released by the earthquake. The quantity 10 raised to 4.40 joules is the energy released by a very small reference earthquake. For example, suppose that an earthquake released approximately 10 raised to 12 joules of energy. What is the magnitude on a Richter scale? How much energy does the earthquake release than the reference earthquake? Solution: given is the energy is 10 raised to 12 joules. Using the Richter scale formula, that is R is equal to 2/3 log times E over 10 raised to 4.40. So R now is equal to 2/3 log of, change the value of E, which is 10 raised to 12, over 10 raised to 4.40. So log of 10 raised to 12 over 10.40, we're going to subtract that. So that's log 10 raised to 12 minus log 10 raised to 4.40 is equal to log 10 raised to 7.6. So R now is equal to 2/3 log of 10 7.6. And what is log of 10 7.6? That is in base 10, log of 10.76 to the base 10. So therefore, what should be the exponent of 10? So that this will be equal to 10 raised to 7.6. So that is equal to the exponent 7.6. So therefore now, R is equal to 2/3, wherein log raised to 10 raised to 7.6 is 7.6. Multiplying 2/3 times 7.6, we have 5.1, wherein 5.1 is the magnitude in Richter scale. For letter B, this earthquake releases 10 raised to 12 over 10 raised to 4.40, which is equal to 10 raised to 7.6, which is 10 raised to 7.6 equal to 39,810,717 times more energy than the reference earthquake. So we have here the magnitude and description of an earthquake. For magnitude 1, that is scarcely perceptible. Magnitude 2, slightly felt. Magnitude 3 is weak. Magnitude 4 is moderately strong. Magnitude 5 is strong. In the problem that we solved a while ago, that is 5.1, means strong shaking and rocking felt throughout building. Hanging objects swings violently. Magnitude 6 is very strong. Magnitude 7 is destructive. Magnitude 8 is very destructive. Magnitude 9 is devastating. In March 11, 2011 at 2:46 p.m., a 9.1 magnitude earthquake takes place 231 miles northeast of Tokyo at a depth of 15.2 miles. The earthquake causes a tsunami with 30-foot waves that damage several nuclear reactors in the area. It is the largest earthquake ever to hit Japan, and magnitude 10 is completely devastating. The largest earthquake instrumentally recorded had a magnitude of 9.5 occurred in southern Chile on May 22, 1960. It produced a tsunami that killed people around the Pacific Basin in Hawaii, California, Japan, the Philippines, and other locations. Next, we have the sound intensity. In acoustic, the decibel or dB level of sound is D is equal to 10 times log times I over 10 raised to negative 12, where I is the sound intensity in watts per square meter. The quantity 10 raised to negative 12 watts over m squared is the least audible sound a human can hear. So we have here the sound intensity level in decibels. For 0 to 30, that's very quiet. And for 30 to 50, that is quiet. And for 50 to 70, that's moderately loud, like normal conversation. For 80 to 90, that is loud, like the sound of a vacuum cleaner. For 90 to 120, that's very loud, like the power saw or heavy trucks. And for 120 to 130, that is already painful, like the sound of thunder. Then we have also here the example of the sound of a Doppler. For example, the decibel level of sound in a quiet office is 10 raised to negative 6 watts per square meter. For letter A, what is the corresponding sound intensity in decibels? Letter B, how much more intense is this sound than the least audible sound a human can hear? So the solution or the formula is D is equal to 10 log of I over 10 raised to negative 12, wherein I here is 10 raised to negative 6, so we have now D is equal to 10 log of 10 raised to negative 6 over 10 raised to negative 12. Dividing that means we're going to subtract 10 raised to negative 6 minus 10 raised to negative 12, which is equal to 10 raised to 6. So therefore, that is equal to 10 log of 10 raised to 6. So D now is equal to 10 times 6 because log of 10 raised to 6 is equal to the exponent 6. And 10 times 6 now is equal to 60 decibel. For letter B, this sound is 10 raised to negative 6 over 10 raised to negative 12, which is equal to 10 raised to 6, which is also equal to 1,000,000 times more intense than the least audible sound a human can hear. Next, we have the acidity and the pH scale. The pH level of water-based solution is defined as pH is equal to negative log times H raised to positive, where H raised to positive is the concentration of hydrogen ions in moles per liter. Solutions with a pH of 7 are defined neutral, like the human blood, which is 7.35 to 7.45. Those with pH less than 7 are acidic, like the black coffee, the vinegar, soda, stomach acid. And those with pH greater than 7 are basic, like the household ammonia. Example, a 1-liter solution contains 0.0001 moles of hydrogen ions. Find its pH level. Since there are 0.0001 moles of hydrogen ions in liter, then the concentration of hydrogen ion is 10 raised to negative 5 moles per liter. That is 0.0001 is equal to 1 over 100,000, which is also equal to 1 over 10 raised to the 5th power, which is the same as 10 raised to negative 5. So pH now is equal to negative log of H raised to positive, which is H raised to positive is equal to 10 raised to negative 5. So pH now is equal to negative log of 10 raised to negative 5, wherein log of 10 raised to negative 5 is the same as log of 10 raised to negative 5 to the base of 10. So therefore, this is equal to negative 5, exponent negative 5. So therefore, now pH is equal to negative log And 10 raised to negative 5 is equal to negative 5 times negative is equal to positive. So for your activity, write what? For letter A, you're going to rewrite the following exponential equations in logarithmic form whenever possible. That is from number 1 to 5. Then for letter B, rewrite the following exponential equation in logarithmic form whenever possible. That is from number 6 to 10. And for your activity 2, how are logarithms useful? So you're going to read, analyze, and solve the given problems, then show your solution in a separate sheet of paper. That is from number 1 to 3. And that's all for our lesson today. So again, this is Teacher Riza, always saying, stay home and take care of yourself. So please like, share, and subscribe. That's all. Thank you. Have a nice day.